So let's go back to gravitational fields, and this time we're going to do the high-level aspects. Take a step back now and think about the following questions. Write down the answers on your notes. If necessary, go back to your previous SL topic information and revise it. You need to be able to define a gravitational field. You should be able to describe the gravitational force between two masses. You need to be able to state in which direction the gravitational field acts. You should be able to define gravitational field strength, state whether it's a vector or a scalar, and explain how you would represent a field around a mass. Now these are all standard level requirements. So stop, go to the textbook or your notes and do a little bit of revision. I'm going to go over the answers superficially here, but I can't emphasize enough how important it is that you go back and look at your previous material. A gravitational field exists where any mass experiences a gravitational force. Now Newton's law of gravitation is F equals gmm over r squared, where g is the gravitational constant. The two m's represent the mass of the object in the field and the mass of the planet, respectively, and r is the distance between the two objects. This is an inverse square law relationship, and you should remember what that looks like. It's important to note that gravitational forces can only be attractive. Unlike other forces involved in other fields, for example, like the electric field, which we'll come to later. The definition of gravitational field strength. By definition, gravitational field strength is the gravitational force per unit mass. Now by mass, we mean the mass of the object. So we find the gravitational field by dividing the gravitational force, represented here, by the mass of the object in the field. This is, of course, a vector quantity. As force is a vector quantity, it follows that gravitational force would be 2, and it points along the direction of the force stated above. Gravitational fields can be represented on paper by the use of field lines. So on the Earth, for example, you would have a radial field, which would show lines perpendicular to the surface, like this, although better drawn. Okay, so that would be a radial field. We'll look at these later when we come to the topic of equipotentials. So, in a nutshell, this is our revision. Okay, so you have an expression for force, you have an expression, or rather a definition of gravitational field strength, which is force per unit mass, and you use that definition to derive an expression from here to give you gm over r squared. There are other sections to the standard level syllabus, but these are the important ones pertinent to what we're going to do now. Here's a better diagram than the one I did, showing you a radial field. And as you can see here, it's quite clear that we have perpendicular to the surface as our field lines. Field lines, it's important that you remember, show the strength by representing it in terms of the distance between the field lines. What does that mean? The closer the field lines, the stronger the field strength. So what makes high-level fields different? Well, we need to talk about the potential energy in fields to start with. In the past, we've always discussed gravitational potential energy as being simply the mass times the field strength. Yes, it's the same field strength we've been talking about recently, times the height. Now, m is the mass of the object. G is also the acceleration due to gravity. So that's equivalent and equal to the field strength. And h is the height above a defined, chosen zero potential energy point, which is usually and quite arbitrarily chosen as the floor. So if you have an object at a distance h above the ground, we tend to just assume h, or even just change in h, but we still assume that this would be our point of zero potential energy. Okay, so what are the problems with this definition? Now, if we use the function EP equals mgh, we are making the assumption that g, and this is what we always do, is a specific fixed value, 10 or 9.81 meters per second squared. However, the acceleration field, the acceleration due to gravity or the gravitational field strength is not constant. It actually depends on these values. It's a varying function. So this is an approximation that we can only use very, very close to the Earth. We can think of it in terms of field lines as well. If we take a macroscopic look at the planet, that means a big view of the gravitational field of the planet, then the field lines are demonstrating that there is a change in strength. But however, if we zoom into the surface, then what we see very, very close to the surface is that these field lines are actually equally spaced. Now, again, it's an approximation, it's an assumption, but it's a good one, because for a tiny range, which includes the range that we use in these kinds of problems, then they pretty much can be assumed to be uniform. So we need to change this idea for wider views of the planet. So if we're considering the gravitational field on a planet per se, then we have to consider a different idea. The idea of the floor being zero potential energy is also fairly arbitrary. We have to come up with a better way of describing this zero energy point. So this becomes a much better definition. The total gravitational potential energy of a system is defined as the work done when bringing all the masses of a system to their present positions, assuming they were originally at infinity. So this means that instead of thinking about an object being on the floor, lifting up to some point x, we now assume zero potential energy is at infinity, and we consider the amount of energy needed to bring it to that point there. Infinity then is chosen as the place where gravitational potential energy is zero. This is our final relationship then for potential energy. Can you derive the expression from the definition? Using, in fact, our basic idea for potential energy, but adapting it to these new conditions. Try deriving a new expression from here and see what you get. So now we've substituted a relationship for field strength, which varies with distance above the ground. We can now consider a relationship for potential energy. This H now can be considered R, because our reference point isn't the floor anymore. We're not thinking about it in terms of a height above the floor. We're considering the distance from the center of the Earth, and our zero potential energy, remember now, is at infinity. I know it's a bit weird. We will come to that in a minute. So our final relationship is as expressed here. Now in a couple of slides, we will talk about this minus sign, which is very important. Now, just a quick reminder that when we're talking about energy, work done, in particular with regards with energy, you raise an object or you move an object, you gain potential energy because you do work. So the work done in moving an object up and giving it more gravitational potential energy is force times displacement. Okay, so the fact that this is going a long-winded way is irrelevant. What matters is the final displacement. Not something that I've seen in many exam questions, but it's worth taking into consideration. Now let's look at that minus sign. This is an explanation within the textbook, but again it illustrates what I'm saying. As you move something away, as you raise an... The fact that gravitational potential energies are always negative is to do with the fact that the final destination has zero potential energy. Now, it's fairly easy to understand that as you raise an object up, its gravitational potential energy must increase. But it has to increase up to a maximum of 0. Now, I guess the only way you can align those two ideas is by considering the minus direction. Now remember, energy is a scalar, so it's not incredibly important. We don't have to worry about it too much. It's a convention. So if we have 0 gravitational potential here, what we're saying is that the amount of potential energy starts off at the lowest minus value, and then the actual amount increases up to a 0. So if we consider this graph would show us the work done in raising an object or increasing its potential energy. So if you go from minus to minus, what's important about here is the difference between these 2 points of gravitational potential energy. I'll even put some numbers in if it will help. Let's say you've got minus 100 to minus 50. The work that you do would be 50 joules of work. So it makes sense. And then the amount of work you would take to move it into infinity would be its actual final value. Okay, so it would be minus 100. You'll realize just how straightforward this actually is when we do some questions. Now, I'll give you something to practice. Work out the gravitational energy needed to bring a 1 kilogram mass to the surface of the Earth from infinity. I'll even be super generous and tell you that the radius of the Earth is 6,371 kilometers, and the mass of the Earth is 5.97 times 10 to the 24 kilograms. Here's your answer, see if you can get it. So now we're going to define a quantity called gravitational potential. Now the gravitational potential is defined as the work done per unit mass in bringing a small test mass from infinity to that position. So pretty much what we're dealing with is potential energy, because that's what potential energy was. The work done bringing an object from infinity to some point x. Now what is different about this is that it's the potential energy over the mass of the object. The work done, remember, and the potential energy are equivalent to each other. So I'm referring to potential energy because that's the expression we have just been working with. So now all we have to do is divide potential energy by the mass of the object. And that gives us an expression for potential, which is potential energy per unit mass. Potential is given symbols of Vg and has the units of joules per kilogram. I'm not referring to electric field issues just now. I'll come to those later. And we're just going to stick to the gravitational field theory. it's important also to remember that potential is a scalar quantity. Now stop the video and try and derive an expression for potential in terms of the mass of the planet. Okay, so potential in terms of the mass of the planet and the position of the object in the field. Okay, so that's simple enough. We have the potential energy, which is G m over R, but it's per unit mass. So of course these two cancel out and we end up with G m over R. Okay, and that's how we work out potential. Try a few questions now to learn the formulas. Now, just as a little appendix, I'm going to talk about potential difference. Now, you came across potential difference in electric current, and it's going to make a lot more sense to you now when we cover this in the next section, which is electric fields. But now you know what potential is, Vg. You can understand or appreciate what potential difference is. The potential difference between 2 points is the work done when moving a unit mass between those 2 points. So we're looking at a delta H here. And that would give us, in our relationship, Vg, if we're looking at potential difference, it would probably be Gm over delta R. So again, not something that comes up very often, but it's important to appreciate the difference. Potential difference and just potential on its own. So now just appreciate that difference by trying this next question. Equipotentials. A field line, which we've come across before, represents the direction of force on a mass. If the field lines get closer together, it means the field strength is increasing. So the field lines represent which way the force is acting on an object. It will tell you which way it's going to go if the force is acting. So what are equipotentials? Equipotentials are points in the field which have the same potential. And remember, potential is the amount of energy, potential energy, that an object has per unit mass. So it's points along a field that would require the same amount of energy to get to. Now, equipotentials have rules, and they're very easy to draw if you follow those rules. Now, gravitational field lines are always perpendicular to equipotential surfaces. That's the first thing. So when you're drawing these equipotentials, usually what happens is the field lines are there already. So you have to make sure that the equipotential points not only are marking places of equal potential, but that when you draw the field lines, the equipotential, you make sure that there are 90 degrees to the field lines. So that's the first point, the perpendicular aspect to it. The second one is they always point from high potential to low potential. So in this case, the field lines are going towards the floor, which is at a lower potential. Now that's when that minus thing can get really confusing, but remember, potential is a scalar. So by lower potential, we mean magnitude, lower potential in magnitude. Here are some examples of some equipotential lines, and they're quite interesting when the field lines are not present. The field lines would be radial in that sense. And as you can see, they show that the field strength is much stronger because even the equipotentials are closer together.